Good morning. My name is Emily Leproust. I'm the CEO and co-founder of Twist Bioscience, and it's a pleasure to talk to you today. A few. Is it coming? So while they load the slide, a few words about Twist Bioscience. We were founded in 2013, so actually 4 years old. The time flies. We have 3 sites. We have a site in San Francisco, one in South San Francisco, and we have a research center in Tel Aviv. And so far, we've raised $166 million and counting. What we have is a technology that is based on silicon, and the idea is to provide a game-changing throughput, speed, cost, and quality. And basically what we've done is we've miniaturized the chemistry, and right now we've miniaturized the phosphoramidite chemistry, but we can't wait to miniaturize the enzymatic chemistries that are coming. And on a silicon chip that is the size of a 96 well plate, we can synthesize 10,000 pools of 100 oligos and turn those into thousands of genes at the same time. So what we want to do with that is enable you to solve the humanity's grand challenges. One of them is sustainability. Everything we touch every day is made from oil, and through the re-engineering of yeast or E. coli or algae, we'll be able to make the same chemicals we use and even better chemicals using sustainable resources. We also want to enable people to solve any hunger issue and make sure that the entire population has food security and great nutrition through the modification of plants. And finally, probably more important more important to I'm going to switch. More important to this room, the understanding, the diagnosis, and the curing of diseases. So how do we do that? We do that by providing DNA at scale, and I'll go through what we offer. I will skip the data storage part for now. So first we offer genes, and so we can get clonal genes from Twist. As you can see, they are 100% NGS verified. It's your gene, your vector, and we can make them up to 3.2 kb at this time. And the first base starts at 9 cents per base, so it's really inexpensive, and we have massive scale to do that. If you still like to clone yourself, you can get fragments, and they have less than 1 error in 3,000 base pairs, and you can get them for 7 cents. So we're in business, and this is the actual production data over the last year. And so in green, you can see the number of genes that we shipped. And in all of 2016, we shipped 35,000 genes. And in the first quarter of this year, January to March, we shipped 31,000 genes. So we're at an average of 10,000 genes per month. And we anticipate to go to 60,000 genes per month at the end of the year. I cannot overstate how humbling it is to actually ship 10,000 genes per month. The silicon is great, but it takes a lot more software than you think it does. I thought I would start a biotech company. I'm actually running a software company at this point. So that's the raw throughput in terms of turnaround time. In dark green, I'm showing the turnaround time that we achieved in 2016. It was an average of 26 days, and it was a wide distribution. And in green, you can see what we've achieved in January to March, and the distribution is tightening, and the average dropped to 19 days. And in April, we were able to achieve 15 days turnaround time, so we're now way to getting to 10 days. So if you want genes, we got them at scale. We also want to enable CRISPR applications. Guide RNAs are about 150 base pairs. We can make millions of them at the same time. We make oligo pools for CRISPR screens, and you can get as low as a few hundred guides or as high as thousands. They are very high quality. They are very uniform, so you can minimize the amount of screens that you have to do. Just a few words about drug discovery. We also do antibody libraries. People are used to doing a random mutagenesis, and you basically have to find a needle in a haystack. And with us, you can just send us the actual sequence you want, and we'll make it from scratch explicitly, so you can make a stack of needle. And we are able to make saturation mutagenesis libraries and combinatorial libraries of variants up to 10 to the 10. Just a quick data point that we got from a customers. They compared saturation libraries from Twist versus a library made by error-prone PCR. They found 10 hits. With Twist, we got all 10, and with error-prone PCR, they only found 2 out of the 10. So by making synthetic antibody libraries, you can do less work and get more hits. So what we need to do now for the Human Genome Project, what we've heard is that people need scale, they need cost, they need to be able to assemble DNA from kilobases to megabases and even gigabases, and then get to the cellular localization. And we think we can do scale and cost. This is what is available today. And you can get non-clonal fragments. If you want 100 megabase, if you want to make a big project, you can get 100 megabase for 2.9 cents per base today for non-clonal if you want to clone yourself. And if you want us to do cloning, you can get to 5.5 cents per base. So hopefully that enables people to have scale and cost. And then for the assembly, you should talk to Pingyang, and for the cellular localization, you should talk to Leslie from earlier. I think others will do that. But we definitely are here to provide a scale and cost. So with that, I will save some time for the next speakers, and happy to answer any questions. Any questions? Jeff?
If people order parts that are within your guidelines, what's your current percent delivered on the first go-round?
So the first pass yield for clonal gene is 90%. So first pass 90%. Second pass, usually you can get another half of that. And then the last 5%, usually there is something biologically wrong with the sequence, and so just cloning, it's toxic.
And that's true for the 3.2 as well as the 1.8?
So yeah, we have a slightly different process for the 3.2, and we actually have a higher yield with 3.2 than with the 1.5. And then for the non-clonal, it's basically 100%. The non-clonal fragments, unless there's a very big repeat and there's misassembly, but those we can filter them out in silico before. So we will tell you in advance, look, we can't make that because it will misassemble. So basically 100% for non-clonal and 90% for plus for clonal.
So for the clonal fragments, I assume you're still cloning it through E. coli, right?
Yes. Yeah. So
do you have plans to go to any sort of like in vitro cloning?
So absolutely. So right now, yes, it's and that's why we still do have sometimes toxicity issues where just the vector or the gene is toxic to E. coli. Right now, it's 100% through E. coli, but we're looking at ways to get out of it, just to recover those that biological toxicity, take it out. We are not there yet.
Hi, Emily. Thanks for your talk. Just out of curiosity, how long would it take your facility to produce all 3 gigabases for a human genome?
3 gigabases. So at 60,000 at the end of the year when we're at 60,000 genes per month. That's they're all 3 kb. That's 200 million bases a month. So it's maybe a year's capacity to make 3 gigabases clonal. But if we know it's coming, I'm just gonna go raise more money, buy more machines, and so at that point, it's just a scale issue. It's very easy. So please bring in a 3 KB, no problem. 3 gigabits. There are no more questions. Thank you very much.